Welcome to the lecture on regression. I've split it into two parts because it's very long, and so it makes it easier to download. I'm going to do a little bit of what I call a bird walk and review statistical significance. Then I'm going to talk through the regression equation, talk to you about error, and in the second half I'm going to go through an SPS example. Remember that in statistical analyses, we always put forth the null hypothesis that there's no relationship, no difference, or no effect in the sample that we are working with. Then we use the results of our analysis to either accept and keep that null hypothesis or to reject it. In other words, if I'm researching the relationship between poverty and bike helmet wearing in elementary children, I start with the null hypothesis. Then I try to show that this null hypothesis should be rejected. Before we do an analysis, we decide on a significance level, kind of like a line in the sand we are going to use for accepting or rejecting that null hypothesis. We set a standard for how likely we are to reject that null hypothesis when we should not. A common alpha is 0.05 or 5%. When I report that there was a strong negative correlation between poverty rates and bike helmet wearing rates with a p less than 0.05, I'm saying that statistically there's less than a 5% chance that I'm rejecting that null hypothesis when I really shouldn't. When I report my results, I always include a statement about the statistical significance and give the probability. Here's one pretty typical example of how I could write up what I saw with the correlation between bike helmet wearing and poverty. And here's an example of how it could be written up when it's not statistically significant and you're not going to reject the null hypothesis. Just some quick reminders about how to report this. And this is based on APA style. Use the exact probability unless it's less than 0.001. So for example, if your SPSS printout or output says that the statistical significance is 0.000, then you report that as less than 0.001. You don't ever report it as p equals 0.00 because you're never going to know exactly what that probability is. That's the signal that you know that it's at least less than 0.001, which is pretty small. If your alpha is set at, say, 0.05, and you've clearly spelled that out in your write-up, or 0.01, as long as you've clearly spelled out what it is okay to report whatever the probability is as less than 0.05. So if it's 0.02, it's okay to say that it's less than 0.05. If it's greater than 0.05, report the exact value and round it to the hundredths. Just a quick side note that we always italicize these letters for things like correlation or t-tests or the F statistic or the P. So you always italicize those when you are writing them out. Let's look at regression now. Remember my example of bike helmet wearing elementary students. There was a relationship between the rates of poverty and the wearing of bike helmets. When the rates of poverty increased, the wearing of bike helmets went down. With regression, we say that the percent of free and reduced lunch on the x-axis is the predictor variable, and that the y variable is the criterion variable. I can see the trend that these data points make. So I can draw a line to represent the trend. This is a regression line. It's an imaginary line. It's a mathematical line that I draw. And what that line predicts is where the data points should actually be. So I can use it to predict the percent of children wearing bike helmets for a poverty rate that's not in my data set. Say I want to predict what percent of the kids will wear helmets in a school that's at 40% free and reduced lunch rate. So there's where that 40% would cross this prediction line, And if I extrapolate that over to my y-axis, it looks like the percent would be about probably 25%, maybe a little bit higher than 25%. But the catch is that I have to figure out where to put that line so that I can best predict and have it fit with the data that I actually have. There are many possibilities of where I could put that line. The most accurate regression or prediction line goes where I can show an average change in y as x changes. This is called the method of least squares. By the line representing the average changes in y, I'm actually putting it where the average distance from each point to the line is the shortest overall, considering all of the data points that I have. If I measure the distance from each data point to the line, either down to it or up to it, I'm putting the line where it's the closest fit to all of the data points that I have. The regression line can be represented as an equation too. This equation should look pretty familiar from your algebra days. Let's look closer at the slope-intercept line. In high school, you probably worked with the equation of a straight line. But when we're describing a regression line, we're using different symbols. First of all, we use a y with a little hat, and it's actually called y hat. And that represents the value of y that you want to predict. Whenever you see that little hat, you know that you're trying to make a prediction. Remember, that's your criterion variable. It's the variable that it's the value you're trying to predict based on some value of x. So next you need to know the slope or the steepness of the regression line. Your b tells you the slope. If the slope is 1, it means that for every unit I move to the right, I go up 1. There's a slope of 1. If you have a slope of 0.5 or 1/2, it means that for every unit you go to the right, you're going up a half a unit. And there's the slope for 0.05. You can see the difference in a slope of 1 and a slope of 0.5. So can you picture what a negative slope is going to look like? I'm going to draw a slope for a negative 1.5. My b would equal negative 1.5. That means that for every unit to the right that I'm going down 1.5 units. And there's my negative slope of 1.5. So your b is going to be positive, or it's going to be negative. Back to the regression line then. You multiply the value of x that you were using as your predictor data point by the slope. You'll recall in this example, I wanted to predict the helmet wearing with 40% free and reduced lunch. That 40% is my x value. Finally, I add the value for where the line crosses the x-axis or the y-intercept. In this example, the y-intercept is 1. In this example, the y-intercept is 4. The y-intercept can actually provide valuable information. For example, if I'm comparing the increase in income between two groups, which group would you rather be in? The group that started at a y-intercept of 22,000 made great gains. But it's important to look at that y-intercept and see that they never caught up with the group that started or had the y-intercept of 50,000. So you can see that we use y-intercept a lot when we're comparing two different groups and how different they are and how different their change over time can be. Okay, let's predict. Oh, my prediction line got kind of crazy there. Let's predict the percent of students likely wearing helmets using the regression line equation instead of my really poor diagram here. Here's the regression equation for this particular case. The slope is negative 0.59 and the y-intercept is at 50%, or 0.5. All I do is replace the x variable with the value of 0.40, or the 40% that I want to see. And when I solve it, I find out that my predicted y value is 0.264, or 26.4%. Now, if you've got standard scores, it's even easier to predict a standard score from a standard score. So if I want to predict the standard score for a particular x, the standard score for an x, all I have to do is multiply it by the correlation. So that one is really, really simple and easy to do. So let's talk about the method of least squares a little bit. Remember that the regression line is fitted by the method of least squares. We need to square the differences between where the data points actually are and where we would predict they would be, which is my red line, my regression line. Notice that very few of the data points are actually on that line. That's because they're actual data points. They're not predictions. The predictions will all be on that line. So let's look at this data point right here. It represents 11% free and reduced lunch. If I were to predict the helmet wearers for 11% free and reduced lunch, I would predict that 43.5% of the kids would be wearing helmets, which is right on my prediction line. This that I've shown here, this difference between a data point and where we predicted that data point would be, is known as the error. A lot of things could contribute to that error, and I'm sure that you can think of many of them. But error is the distance from the actual point to what we predicted. Now your textbook goes into great detail with these formulas for finding the slope. And it's good to practice the math on this and see if it makes any sense to you at all. The first step is to find the slope, which is also known as the regression coefficient. Then the second step is you find the y-intercept, which is your regression constant, and then you simply put it into the slope-intercept form. Now, if you're going to use these formulas, this shows you where each of the pieces come from. You're going to have to make a chart like this and figure out what your x squared is for each value and your x times y, and come up with a sum for that. You'll need the mean of the x and the y if you're going to work through getting your slope, or not your slope, your constant, with the easier formula. Doesn't matter. So you'll need to plan on doing that. Last of all, you need to be able to calculate that the standard deviation, or how close those data points are overall to your prediction line. It's just like looking at the variability, only we call it the standard error of estimate. Basically, you're calculating the amount of variance not explained by the correlation between x and y. So that error is measuring all of the things that aren't explained by the percent free and reduced lunch.